And the very last talk this morning is by Peter Kosec, who will talk about ionized emission in a large sample of ultraluminous X-ray sources.
Hi, everyone. First of all, thank you. Thank to all of you who stayed who are sticking around for the last talk of this conference. I'll be continuing to talk about ultraluminous X-ray sources. I'll be focusing mostly on the spectral analysis of these objects. As the speakers before me said, nowadays we know that a majority of ULXs are powered by super Eddington accretion onto stellar mass compact objects, which definitely includes neutron stars, might also include stellar mass black holes. And we know that this accretion happens without extreme beaming because we observe many ULXs embedded in these huge ionized bubbles, hundreds of parsecs large, which indicate that the luminosity truly is extreme. Additionally, unless all of these objects are very highly magnetized neutron stars, some part of the accretion flow will be supercritical, and therefore it is expected to launch these powerful radiation-driven winds, which might be detectable. So we can expect to see in these spectra some emission lines for material out of our line of sight, as well as some absorption lines potentially from this wind. Now the question is, can we detect these features? The problem is that despite the larger ULX luminosities, the X-ray fluxes of ULXs are quite low since they are located in external galaxies and therefore at megaparsec distances. Fortunately, we know of a couple sources which show, which have good enough X-ray data, and they show where we can directly detect these emission and absorption lines. Here, I'm showing the first example, which is NGC 1313X1, where Pinto et al. Were able to obtain a high-resolution X-ray spectrum with RGS spectrometer on board at XMM Newton, and they detect these highly blue-shifted absorption lines from a couple elements, including neon, iron, and oxygen, which point to the presence of a very fast disk wind with a velocity of 0.1 to 0.2 speed of the light. At the same time, they detected these narrow emission lines, which come from the same set of elements, again, and point to some lower velocity material out of our line of sight, which is quite highly ionized. So therefore, this is quite a complex spectrum, as you can see, where we have to resolve the absorption lines from the emission lines from the continuum, and therefore we need high spectral resolution. We need X-ray gratings. In general, CCD instruments have moderate resolutions which cannot resolve these lines, making this problem more complex observationally. Now, another quite exciting recent result is NGC 247 ULX1, which is a spectrally very soft and very variable ULX, which shows both emission and absorption lines in the X-ray spectrum. None of these lines, in fact, appear to be completely rest frame. So Pinto et al. Have recently obtained a large XMM Newton campaign on this object, and they performed a large systematic search for both absorption and emission simultaneously. So what I'm showing in these two plots here is a systematic search for photoionized emission and absorption. They created many photoionization grids which sample a large range of photoionization parameters. And a large range of outflow velocities. And then they fitted all of these possible photoionization grids to data and recovered the best fitting photoionized emission and absorption properties. So these plots look a bit degenerate, but in fact, the best fitting parameters are quite constrained. And they show that the photoionized absorption is moving with a velocity of about 0.17 speed of the light, while the photoionized emission is receding with a velocity of 0.04 speed of the light. So this could be some kind of a p-signy feature where the absorption is blue shifted while the emission is red shifted. However, I need to note that the line widths of these features are not very large. So it is not a very traditional p-signy profile where both absorption and emission part is very broad. Now, so these were a couple examples of ULXs which have the best quality data sets, but now the question is, are they representative of the whole ULX population? To investigate this, we decided to study all of the ULXs that we can currently. We collected all usable archival observations of of 17 ULXs in total with the RGS grating spectrometer on board XMM Newton. This was almost 100 observations in total, some of which we had to stack per object to achieve better signal to noise ratios. Then we decided to search for any narrow plasma signatures. So we searched for any narrow spectral lines, either in emission or in absorption in this spectra. Our preliminary study from 2018 performed simple Gaussian scans where we took the RGS spectra and then we fitted Gaussians at all of the possible wavelengths, then recovered the fit improvements, which tell us how likely there is a line at each of these wavelengths. What we found is that several of these ULXs show rest frame oxygen emission, either in the oxygen 7 triplet or in the oxygen 8 line. So this is quite similar to what has been found in these couple ULXs with the best quality spectra. Now, we developed a completely new search method to decrease the computational expense of this search across all of the 100 observations. It is similar to just performing automated direct fitting by putting a Gaussian of any parameter of any wavelength or any width to the spectrum, but instead it is based on cross correlations between the spectral models and the data. Now, to accurately and rigorously constrain the significance of any line detections, we perform the same searches on simulated spectra of each of these observations. So we perform 10,000 simulations for each observation, and then the false positive rate determines the significance of any line feature detected. So then we collected all of the 135 line detections, strongest line detections, creating the first catalog of spectral lines in ULXs. We find that almost all of these observations show at least one line detection, and about a third of these observations show at least 5 line detections. So it seems that plasma signatures are a quite common feature of ULXs if we have good enough spectra to detect them. Now, here are the wavelengths of these lines. Here I'm showing just a histogram of the emission and absorption features detected and their wavelengths, this is from the full sample. What we find is that the emission features are strongly concentrated around the rest frame transitions of known elemental transitions, such as magnesium, neon, iron, oxygen, and nitrogen. So these come from some low velocity material, which is still quite highly ionized and might not be related to the accretion, disk wind, and absorption. Now, instead, the absorption lines seem to be avoiding these rest frame transitions. This is best visible in the oxygen transitions and some of the iron and neon transitions. Instead, these absorption line detections are concentrated in between the rest frame transitions, and then therefore they should be they're probably shifted from the rest frame. Therefore, they are fully consistent with highly blue shifted absorption with velocities of 0.1 to 0.2 speed of the light from very fast winds. Therefore, it seems that fast winds are a common occurrence among the ULX populations. Secondly, we investigated how the occurrence of line detections varies with other ULX parameters like the hardness ratio or the X-ray luminosity. So we counted the number of significant line detections per observation and plotted them versus these two parameters. And we find a strong anti-correlation between the number of light detections and the spectral hardness of the ULX. This is not a data quality effect. We can see a significant anti-correlation even if we split the sample into two parts, one like higher data quality part and lower data quality part. And we also see this anti-correlation for emission and absorption lines separately. Now, on the other hand, we see absolutely no correlation between the number of line detections and the X-ray luminosity of the ULX. Now, these trends are very intriguing considering what a ULX system might look like. Here I'm showing just a possible schematic of this ULX, of a general ULX. If a ULX has a supercritical accretion flow, it should look very different. It should have a very different appearance depending on the inclination angle of the observer. So in general, we think that if we see a ULX more face on, we are looking directly into the inner accretion flows regions, which are very hot, and therefore it should have a hard spectrum. Instead, at a higher inclination angles, these inner accretion regions could be obscured by the thick accretion disk, or some of this hard X-ray emission from the inner region could be downscattered by the wind.
3 minutes.
Okay, thank you. So So these trends are very interesting, and of course, this schematic can explain readily why the absorption features might be missing from the harder ULXs, simply because this accretion disk wind might not be crossing our line of sight towards the X-ray source in the more face-on sources. However, it is more difficult to explain the disappearance of the emission features. If this was a pure inclination effect, the emission features should always see the same SED of the ULX despite the inclination of the system. It is not plausible that these emission features would be obscured in the more face-on sources. One could argue that in the more face-on sources, the inner accretion regions might simply outshine the emission line emission. The emission lines, which are softer, but then again, we do not see any anti-correlation between the line occurrence and the X-ray luminosity of the object. Therefore, we think that these trends, the anti-correlation with the hardness, simply cannot be explained by purely different ULX orientation, but we need another factor which is driving these trends. One possibility is, of course, that it is different mass accretion rates. In general, if the mass accretion rate of a ULX is higher, the scale height of the thick accretion disk could be higher, therefore closing the funnel and creating a generally softer SED. Therefore, harder SEDs of the ULXs with lower mass accretion rates could over-ionize the emission lines, making the line strengths weaker, and therefore making the lines harder to detect and create less line detections in the data that we have. Now, instead, it could be due to, if all of these objects are instead neutron stars, it could be due to different magnetic field strengths in these objects. In general, the magnetic field strength of the ULX of the neutron star will define the size of the magnetosphere and how much the accretion disk is truncated. Then the size of the magnetosphere will define the ratio of, or the contribution of the accretion column to the accretion disk luminosity, and then somehow drive the spectral hardness of the object. And it could also drive how much mass is actually going into the outflows by driving how much the disk is being disrupted. At this stage, however, we cannot discern between these two possibilities. Now, just to quickly summarize, if we look at the high-resolution X-ray spectra of ultraluminous X-ray sources, we find a plethora of emission and absorption plasma signatures. The emission lines appear to originate from rest frame plasma, while the absorption is consistent with fast outflows crossing the line of sight. Additionally, we found a strong anti-correlation of a line occurrence with the ULX spectral hardness, which could either be explained by differences in mass accretion rates of soft and hard ULXs, but not by purely varying inclination angles. And that's all from me. Thank you for your attention. I'll take any questions.
Thank you, Peter. So do we have any questions in the room? I don't see any. Yes. We don't hear you.
Yeah. Can you hear me? Yeah.
Yes.
Yeah.
Yes. So very nice talk. I have a simple question. I don't know. Did you check, for example, the link with the possible presence of instabilities, or the link with the thermal instabilities of your flow that you may have? Is there any link with the presence or absence of absorption lines and so on?
So we have done an analysis that is as model independent as possible in this work. So we simply just collected all of the emission and absorption features detectable. We have not compared them with, for example, the SED of the object. But actually, there was a paper from Ciro Pinto from a couple of years ago who looked exactly at this, and they did find some possible instabilities, which could be driving the appearance and the disappearance of these features. So this is, I guess, Pinto et al. 2020.
Okay, thank you.
Do we have an online question? I don't see any on the Slack either. Just the Slack will remain open for, I guess, another couple of weeks anyway. So there is plenty of room for exchanges even after the conference. So don't hesitate to continue on and ask questions and think you want to be cleared. No more question in the room?
No, no more question here.
So I guess we can thank Peter again.